Hello everyone. I once again welcome you back to my YouTube channel. This is going to be my second lecture on the topic of electrostatics. In the previous lecture, I have talked about electric charges, properties of electric charges, Coulomb's law and superposition principle. Continuing, we are going to develop a notion of electric field. What is this electric field? Electric field is said to be a region of space around a charge or a system of charges which when other charged particles enter, they experience a force. Now, this term electric field, rather field, generally refers to a quantity that is defined at every point in space and may vary from point to point. If it doesn't vary from point to point, then the field is said to be constant, or in other words, we can call it as a uniform field. If it varies from point to point, then we will call it as non-uniform field. Mathematically, any field must extend up to infinity, but practically an electric field is detected up to a limited distance. Coulomb's law encourages us to think in terms of action at a distance. What does this actually mean? It means that there is a charge. Around the charge, it creates a space called electric field. And when other charges enter this particular field, they're supposed to experience a force. So therefore, the problem of determining interaction between any two charges is reduced to two separate problems. The first problem is to determine electric field due to first charge, and the second problem is to calculate force on this charge the field exerts using the concepts of Newton's laws. So let's define what electric field is concretely. Electric field at a point, electric field at a point due to a source charge is a force acting per unit positive test charge placed at that point. The few terms, that is source charge and test charge. Mathematically, we can define electric field as force experienced by unit positive test charge placed at that particular point. It is given by E is equal to F by Q naught, where F is the force acting on this test charge and Q naught is the magnitude of test charge. SI unit is obviously force is Newton and charge is Coulomb, therefore it is Newton per Coulomb. Above definition, as you can see, presence of electric field is detected through unit positive test charge, not unit positive charge. What do we mean by this test charge? And why do we need this test charge? This is because by assumption that test charge does not alter the electric field we are defining. Meaning, let's say I want to define electric field due to a particular charge. I will call this as source charge. And this charge is supposed to create electric field, as I've already remarked, right? And if I have to find the strength of this electric field, I have to bring in something called as a test charge. Test charge. A test charge, by an assumption, it doesn't have its own electric field. If I bring in a unit positive charge, it is going to alter the strength of this electric field here, because as you can see, if I bring a positive charge, it ends up repelling the source charge, right? So we don't want any such disturbances happening. So we introduce the concept of test charge, and this test charge by assumption does not alter the electric field strength of a source charge, which is supposed to be creating electric field. Now the next question is, why positive test charge? There is nothing wrong in considering a negative test charge. Only change is the change in direction of force. Take a look at these two figures. We have a source charge which creates an electric field which is outward in nature. Now once I bring in a test charge, a test charge which is unit positive test charge, it is going to experience force in the same direction. Now, if I bring a unit negative test charge on the other hand, what is it going to happen? It is going to see you're going to see that force is experienced in the opposite direction to the direction of electric field. So my advice to you students would be to stick to what is there in the NCERT textbook when you're writing in your second PUC exam. It's better to stick with the force acting per unit positive test charge rather than writing unit negative test charge. Conceptually, there is nothing wrong. Only thing that is going to change is the direction of force. Moving on, we are going to look at the expression for electric field due to an isolated point charge. As we've already remarked that a point charge or a charge in general or a system of charges, they're supposed to create an electric field. Now let us have a mathematical expression for this electric field. Take a look here. I have considered a source charge whose magnitude is plus Q, Q in capital. To test the electric field strength of the source charge, I bring in a test charge of magnitude Q naught and I place it at a distance of R from the source charge. As you can see, the direction of force and electric field are in same direction. They're in same direction. Now, because this charge has been placed at a distance R, we can find the force acting on this particular test charge using the concept of Coulomb's law. From Coulomb's law, we see that F is nothing but mod of Q naught by 4 pi epsilon naught R square, where Q is a magnitude of source charge and Q naught is the magnitude of test charge and R is the distance between source charge and test charge. Let's call this as equation 1. By definition, we have already defined mathematically that electric field is E is equal to F by Q naught. That is force acting per unit positive test charge placed at that point. So in the light of equation 2, equation 1, in the light of equation 1 and 2, what we end up is electric field is going to be Q by 4 pi epsilon naught R square. Q naught cancels off here and we end up with Q by 4 pi epsilon naught R square. Meaning that electric field due to a isolated point charge is proportional to 1 by R square. It falls off proportional to 1 by R square. And vectorially, we may write, because electric field is a vector quantity, one has to define both magnitude as well as direction for a vector quantity. One can write Q by 4 pi epsilon naught R square R cap. What is this R cap? R cap is the unit vector which indicates the direction of electric field, and by definition, electric field of a positive point charge always points away, and therefore one can show this in the diagram. For a positive point charge, the electric field is radially outward. If you consider a negative charge, electric field is going to be radially inward. This is the direction of electric field. So we see that electric field due to an isolated point charge is proportional to 1 by R square. It's very important to remember this expression, as we will be utilizing these expressions in solving problems and doing a bunch of derivations. And the concept of electric field due to a positive point charge always points radially outward, and for a negative charge it points radially inward is also an equally important concept that you will have to remember. Moving on, the next concept that I would like to introduce is the concept of electric field lines. What are these electric field lines? Electric field lines help us to visualize electric fields. English scientist Michael Faraday introduced the concept of field lines and called them lines of force, but term field lines is preferable. I'll tell you why. Because as we progress, you'll see that a few textbooks such as Halliday-Resnick In the previous editions, they have called it as lines of force. I don't want to confuse you by talking about it right now. Keep a hold on it. We will talk about it in the next lecture. Now let's get to the properties of field lines. What are these properties of field lines? And it's a very important question from your second PUC exam point of view. The first property of any electric field line is said to be that it is an imaginary line or curve drawn through a region of space so that tangent at every point is in the direction of electric field vector. What does this mean? We have a field line here, right? This is a field line. It's an imaginary line, of course, and it is drawn through a space. So whenever you draw a tangent at every point of this curve, the tangent is supposed to indicate electric field vector, meaning it is supposed to give the direction as well as the magnitude of electric field at that particular point. So this, in a way, the concept of electric field lines help us to visualize electric field, which is an abstract quantity. We will try to visualize it through electric field lines. So it's an imaginary line or curve. Whenever you draw a tangent to that particular curve, you end up with the direction and magnitude of electric field vector, which is as shown here. At this point, electric field is a tangent and it is pointing upwards. And at this point, it is pointing downwards, right? So one may draw tangents at different points and end up with the direction and magnitude of electric field. The second property of electric field lines is field lines never intersect. If they did, there would be two independent directions of electric field, which is totally absurd. So at any given point, you should have only one direction and magnitude of electric field at every point of a field line. Therefore, you can never have two field lines intersecting each other. The third important property of electric field lines is field lines do not form closed loops. This is because of the conservative nature of electrostatic fields. The conservative forces, you've already studied about conservative forces in class 11, and you've already found that gravitational forces are also conservative in nature. What are these conservative forces? Conservative forces mathematically one can define a potential energy function. If you have a force, a conservative force, one can define something called as potential energy function. We'll talk about this in the next chapter. Whenever you have a conservative forces, please remember that one can always define a potential energy function and a potential formulation is possible. Just like gravitational potential energy, we are going to also have a concept of electrostatic potential energy, which we will be talking in the next chapter. The fourth important property of field lines is field lines are close when field is strong and farther apart when it is weaker. This means to say, more the number of field lines, the stronger will be the electric field. If you have less number of field lines, what do you have? You will have a lesser or a weaker electric field rather. So summarizing the four properties, if you draw a tangent to a field line, you end up with the direction and magnitude of electric field. The second property is field lines never intersect. Field lines do not form closed loops, and field lines are stronger wherever the field is strong, or rather field lines are closer where the field is strong and farther apart when it is weaker. I have drawn few field line diagrams in case of positive charge, an isolated positive charge, negative charge, two positive charges and a dipole. Take a look at the field line diagram of a single positive charge and single negative charge. As you can see, the electric field vector in case of a single positive charge is radially outwards, and it is shown in the green, right? These are the field lines, and a tangent drawn here gives the direction of electric field vector, and it is radially outward. Electric field is radially outward, already remarked. It is directed outwards. Please keep this in your mind. I'm repeating this once again for your benefit. In case of negative charge, it is radially inward. Electric field vector direction is going to be radially inward. Now, this is a case of two positive charges. You may wonder why these lines are curved in nature here. Some of these lines are curved in nature. These lines are curved in nature because of the distortion or repulsion effect. These are distorted because of repulsion effect. Repulsion effect due to the presence of one more charge, right? So as you can see here, the field lines are also pointing outwards. I would ask students to draw field lines in case of two negative charges, and pretty much you should have guessed it by now. Nothing changes, just that the direction of these field lines will be inward. This is the direction of field lines, but you will still have curved kind of field lines, right? These questions are asked for 2 marks or 1 mark sometime in your board exams, and please try to remember these field line diagrams. Now, the next concept that I would like to talk about is a dipole. A dipole is a pair of positive charges, a pair of point charges rather, with equal magnitude and opposite sign separated by distance 2a. So you have one positive charge here and one negative charge here, and they're separated by a distance 2a. The field lines in case of dipole, field lines start from the positive charge and they terminate onto negative charge. Take a look at these field lines here, 1, 2, and 3. They have emanated from the positive charge and they end up onto the negative charge, right? And to the left of the positive charge, the field lines are radially outwards, and to the right of the negative charge, they are radially inward. And if you were to draw a tangent at this point, what does this indicate? It gives you electric field. Again, a tangent at this point, what does this give you? It gives you electric field, right? So whenever you draw a tangent to an electric field line, you're going to end up with the direction and magnitude of electric field. So it's very important for you students to remember the field line diagrams and properties of electric field lines. It is most often asked question in second PUC exam. Moving on to the concepts of electric dipoles. Many physical systems from molecules to TV antenna can be described as electric dipoles. We've already defined what an electric dipole is. An electric dipole is supposed to consist of a point charges with equal magnitude and opposite sign, plus and minus, separated by a distance of 2a. We are going to take up two questions when we are talking about electric dipoles from the point of view of your syllabus. The first question is, what forces and torques does an electric dipole experience when placed in an external electric field? The second question that we are going to talk about is, what electric field does a dipole itself produce? Before we address the above two questions, let us define a very important vector quantity called dipole moment, which tells us something about the strength of a dipole. Dipole moment is defined as a product of magnitude of either charge and distance between two charges. We've already seen we have one dipole here which is having one negative charge and one positive charge separated by distance 2a. So dipole moment vector is defined as product of magnitude of either charge, that is magnitude is q and the distance is 2a. And vectorially, we may write this as q into 2a in terms of p cap. This p cap is a unit vector which gives us the direction of dipole moment. And by convention, the direction of dipole moment vector is always chosen from negative charge to positive charge. As you can see here, dipole moment vector points from negative charge to positive charge. SI unit of dipole moment vector P. Please don't confuse this P with momentum or pressure. P here has got a very specific meaning in electrostatics chapter, and it is going to be, and we are going to call it as dipole moment. It's not momentum or pressure. So charge is Coulomb and distance is meter. Therefore, SI unit is going to be Coulomb meter. Now, since we've defined dipole moment vector, let us get back to the two questions that we would like to examine. The forces and torque that an electric dipole experiences when placed in an external field, and what kind of electric field does a dipole itself produce. The first question that we would like to address is dipole in an uniform electric field. From your board exam point of view, this is going to be asked for 3 marks. It's a 3 marker, a very important derivation. So what have we done here? We have taken an electric dipole. We have taken an electric dipole here, minus q and plus q, which is being placed in a uniform electric field. What do you mean by a uniform electric field? Something that does not vary from point to point, and rather it is constant at all points in space. So we have taken a uniform electric field and we have taken a dipole. And clearly from the diagram, let's see what are the forces acting on these individual charges. We've already remarked in the discussion, for a positive charge, just a minute. For a positive charge, force, electric field points in this way. Force also acts in the same direction. Force and electric field are in same direction. So therefore, as you can see here, the force on this positive charge acts in the right hand side direction towards positive x-axis. For a negative charge, we've already remarked that the electric field and force are in opposite direction. So therefore, the force on this negative charge acts in the opposite to the direction of electric field. So this is along negative x-axis and that's along positive x-axis. So what's the total effect? The total effect of this is the net force on dipole is going to be 0. The total force on an electric dipole placed in a uniform electric field is going to be 0. However, these forces are acting at 2 different points. They're not along the same line. If you see it, they're not along the same line. One is along this line and the other one is along this line. So in a sense, about the center or the midpoint of the dipole, this kind of creates a couple. One force in this direction and the other force in that direction will create a couple, which leads to a net torque on this particular dipole, and that is what we intend to find mathematically. Net torque about an axis passing through midpoint of dipole. As you know, torque is defined as force into perpendicular distance. It's already written here. So we are going to take magnitude of one of the forces multiplied with perpendicular distance. From this point to this point, from B to C is going to be your perpendicular distance. From B to C is the perpendicular distance. It's clearly what is BC from this triangle, from triangle ABC. BC is going to be 2A sine theta. Now, since force by definition is nothing but Q into E, which is Q is the magnitude of one of the charges and E is the strength of the electric field, we've already defined dipole moment vector, which is Q, dipole moment vector, which is P, as Q into 2A. Q into 2A. Therefore, we may write this equation as tau is equal to PE sine theta. The term sine theta tells us about it is a vector product. Therefore, we may write this as tau is equal to P cross E. So this is the final expression. We are going to take a look at few special cases from this particular expression. If theta were supposed to be equal to 0, then torque will be 0. Obviously, sine 0 is 0. So what does this imply? It implies that dipole moment vector and electric field are parallel to each other, and this corresponds to something called a stable equilibrium. A stable equilibrium position is one in which the potential energy function is at minimum. More about this will come in the next chapter. The concept of conservative forces nature, or the conservative nature of electrostatic field, concept of electrostatic potential energy, concept of equilibrium. We're going to discuss this in the next chapter. Coming back to the second special case, tau is equal to 90 degrees gives us maximum torque, which is tau max is equal to PE. And theta equal to 180 degrees also gives us torque equal to 0. But in this case, P is anti-parallel to electric field. That is, dipole moment vector is going to be anti-parallel to electric field, and this corresponds to an unstable equilibrium. It corresponds to unstable equilibrium. Unstable equilibrium is one in which potential energy function is at its peak. So, since we've addressed the first question, the forces and torques acting on a dipole when you place it in a uniform electric field, notice that the force is 0 only when you place in a uniform electric field. Force is not, may or may not be equal to 0 when you place it in a non-uniform electric field. Alright? In a non-uniform electric field, force is not equal to 0, so is torque also not equal to 0. In a non-uniform electric field. Only in the case of uniform electric field, a dipole experiences torque but no force. In case of non-uniform electric field, dipole may experience force as well as torque. A very important concept to remember. Next question that we would like to examine is the electric field due to a dipole. And here we are going to again take a look at two cases. And these two cases are usually asked as 5-mark questions in your board exam. Either one of them. Both questions are extremely important. Both derivations rather are very important from the point of view of your board exam. The first thing that we are going to do is look at the derivation of electric field due to a dipole on the axis of a dipole. So here we have taken a dipole. Let me change the color to blue or something. Yeah, blue is better. So here we have taken a dipole, right, consisting of minus Q and plus Q. And I've taken a point P which lies on the axis of a dipole. This is the axis, and this point P lies on the axis of a dipole. And this point P is at a distance of r from the midpoint of the dipole. And various distances are written here because the distance between two dipoles is 2a. From the midpoint it is a and a. From the first charge it is going to be r minus a, while from the second charge it is going to be r plus a. Now, to find the net electric field at point P, we are going to use two principles. The first one is to use Coulomb's law and then to use superposition principle. Let us draw a free body diagram at point P. and show the directions of these electric field vectors. At point P, as you can notice here, due to a positive charge Q, the field, as we have already remarked, is going to be vectorially, radially outwards, which is shown here. And due to a negative charge, it is going to be towards the negative charge itself, which is going to be E minus and E plus. So therefore, at point P, the electric field is going to be, the net electric field is going to be the vector sum of E plus and E minus. So therefore, clearly from this figure, we may write electric field at point P is equal to modulus of electric field at due to a plus charge and modulus of electric field due to negative charge. As we have already looked into the expression of electric field due to an isolated point charge, electric field due to an isolated point charge is given by Q by 4 pi epsilon naught r square, where r is the distance. Using this expression and keeping distances in mind, we have from equation 1, we are going to substitute for E plus and E minus. Distance here for the positive charge has already been remarked as R minus A, and for the negative charge, it is going to be R plus A. Therefore, we have Q by 4 pi epsilon naught R minus A the whole square and Q by 4 pi epsilon naught R plus A the whole square. Q by 4 pi epsilon naught is taken as common, and what do we have? We have 1 by R minus A the whole square and 1 by R plus A the whole square. And simplifying this expression with little algebra, what I've done here is I will cross multiply the terms. R plus A whole square goes here and R minus A whole square comes here. And I'm going to write this R minus A whole square and R plus A whole square in a particular fashion in the denominator. R minus A and R minus A multiplied together gives me R minus A the whole square. R plus A into R plus A gives me R plus A the whole square. And utilizing the form A plus B into A minus B, the formula, what is this? This is equal to A square minus B square. So clubbing this term here with this term will give you R square minus A square. This term with this term, it is again R square minus A square. So therefore, denominator becomes R square minus A square the whole square. And the numerator is expanded using A plus B whole square formula. And simplifying, we get Q by 4 pi epsilon naught 4AR by R square minus A square the whole square. Now again, equation 7, I'm going to write it in a particular fashion so that I can introduce the term P. So 4A is written as 2 into 2, which is basically 4QAR by 4 pi epsilon naught R square minus A square the whole square. By definition, this term here becomes a P. So therefore, electric field magnitude at point P, which lies at the axis of a dipole, is given by 2PR by 4 pi epsilon naught R square minus A square the whole square. This is the final expression due to an electric field that is due to a dipole on the axis. And we are going to make an assumption here. For an assumption when R is extremely greater than A, that is, the point lies so far that the distances between the dipole becomes negligible. When we introduce this approximation, what happens here? We are going to neglect this term here. A is neglected because R is significantly greater than A. What happens is R square to the power of 2 becomes R to the power of 4, and 1 R cancels, and what do we end up with? We end up with 2P by 4 pi epsilon naught R cube. So equation 8 represents electric field at point P on the axis of dipole, which I've already told you. Equation 9, on the other hand, is an approximation when distance P becomes sufficiently large compared to the size of the dipole. So you'll have to write it till here, starting from the diagram, so that you get a complete 5 marks. The distribution is going to be as follows. A diagram might get about, let me change the color. For the diagram, you get 1 mark, the free body diagram and the diagram. And for this superposition principle, you get 1 mark. And showing the simplification, how much is that? That's 2 mark. And the further few steps, you get 3 more marks. So this is a very important question, and it has been asked several times in the board exam. Please make sure to